welcome to the podcast. This is Mr. White.
And Mr. Johnson.
And today we're going to talk about refraction. So we want to be careful with our words because we've already talked about diffraction, which is the bending of light around a barrier.
Mm-hmm. We've
talked about reflection, which is the bending of light at a barrier, kind of like a rebound. We've kind of talked about absorption. What's absorption?
Where it absorbs the light.
Right, so it doesn't allow it to pass through. It doesn't change its direction, it just sucks it in. Okay, so we want to be careful when we talk about refraction. And we also want to note that, hey, these are not just light things. Okay, these are wave things, wave phenomena. There we go. Can't spell today. Or yesterday. So, wave phenomena is what we're talking about. And you guys, in your investigation today, you took a laser. Okay, so laser. And you shot a beam of light through the air, and it went in a nice straight line. And it went through this nice piece of really expensive glass called Pyrex. And then it came out the other end. Is that true?
Yep.
Okay. So, I wish I could draw my picture again, so let's do that. Piece of glass is long. Okay. So the laser goes through it at this angle, and then it hits, by the way, in a straight line, it hits this transparent material. Transparent means what? What do you think? What's transparent for them?
Well, you can see through it.
You can see through it. So light can go through, or a wave can go through a transparent material. Does it continue to go along in this nice straight path?
No.
No. What does it do?
Well, it bends.
It bends. And how do we know how much it bent?
Well, it all depends on the material to start with.
Certain
material bends light differently.
Okay, so it could be like glass. It's transparent. It could be water.
Right.
Yeah. A diamond, for all those ladies out there taking conceptual physics. It's going to bend the light, and it could. So, are you saying that diamond might bend the light more than water does?
I would believe so.
Yeah, that is true. So, depending on what the material is, will depend on how much it bends. So, it won't travel on this dotted straight line. What it'll end up doing is it'll change the angle of attack and go at a different angle. And just like the law of reflection, we're going to measure our angle from the normal. Right? Remember, normal means 90 degrees or perpendicular to the surface.
Right.
So this would be my refracting angle. And then if it were to re-emerge on the other side, I really didn't draw a very good picture, would it bend back?
Yeah.
How much would it bend back?
Well, it would be the same thing as we did with the angle of incidence and angle of reflection. But this would be angle of refraction.
Okay. So what you're saying is if this is the angle of refraction, this is the angle of incidence, just like before. It's going to leave, and it's actually going to leave and travel in the original path. So whatever path it chooses, it has to be parallel to the original path because it's back out in air. And of course, air is transparent.
Correct.
So we see here where the light can bend away from the normal, and the angle can get bigger. And we can see where the light will bend towards the normal, and the angle will get smaller. Okay? So, refraction has some requirements.
Right.
Okay? First of all, we have to have at least two different transparent medium.
And medium meaning materials.
Yes, that's a good point. Materials. Okay, so that's Check. The speed of light, this is where things get weird, has to change. So, the reason why the light bends is because the speed of light gets slower in this denser material. So, the speed of light in air is fast. It's like some 300 million meters per second, something close to it. Mm-hmm. It travels a little bit slower in glass and in water, and actually quite a bit slower in diamond. But when it leaves that material and it comes back into the air, it regains its speed, and that's why the angle shifts again, because the speed change. It gets back to about 300 million meters per second.
And all of this changing of speeds is happening almost instantaneously.
And it, well, I don't like the word instantaneous.
I'm trying to think of as far as our perception of it.
Yeah, from our brain and our eyes perspectives, I'll go with instantaneous. Mm-hmm. But you can measure this. There are some YouTube videos out there taken at MIT. They've actually slowed a beam of light down to like the speed of a car. So you can watch it travel through this optically dense material. Right? And it's a very interesting thing to watch, because when you flip the light switch on, the lights come on, and we're like, hey, that's instant. But it's not. It's actually a timed event. But imagine slowing light down so much that you could actually see the room fill with light. Cool. That's what that material has the capacity to do. So we go back to another poor drawing. I should start signing these. They're so beautiful.
Yeah.
Yeah. Okay, so I got my laser beam again. So I'm going to go at a little steeper angle. And I've got to measure from the normal. So this is incident ray.
Now the normal is perpendicular to the
surface.
Okay.
Just like it was perpendicular to the mirror.
Okay.
And in the first semester, perpendicular to the table or the inclined plane or whatever it was. So I'm going to say this is air, and then I'm going to say that this is not air. It could be a piece of glass, a cup of water. It could be anything you want it to be. The speed of light is going to slow down. So so how do I do that? V light gets slower. And because of that, it bends in it bends in and it goes away from the normal.
So what you're saying is, if it goes from a faster medium to a slower medium, it bends away from the normal.
That is correct.
Okay. Right. And then it seemed like when it comes out again, it's going from slower to faster, and it bends towards normal.
Right. So light is fast. Light gets slower inside the block. Okay, it's about to reemerge, and it has to reemerge parallel to the original beam of light because it's re-entering the same material. Now, if it were to enter water or something, then the bend would be different. But if it's going back out into the same material, this is what would happen. So this is the normal. How convenient. All right, so this is a different refracted angle because it bent again. Mm-hmm. So then V light returns to original speed. That's refraction. Mm-hmm. All right. So this is an interesting phenomenon. You've seen this before, I would argue. You have seen a glass filled with water that had a straw in it, right? And so as the straw is in it, you don't see this. You don't see, actually that's kind of what you see. You don't see a nice uniform straw the same thickness throughout, do you?
No.
No, you see something else entirely. You see a straw that appears to be broken into 3 segments, and part of the straw appears to be magnified. And so you see, hey, I have this section of straw, glass, water, okay? You have this section of straw, air, glass, and then you have the third section of straw, which is just the air. This is the property of refraction. When I was a kid, I would be swimming, and I'd go to the bottom of the pool to try and get the brick, and I would always line it up. I'd say, okay, I got to dive to right, I got to dive to this spot right here. I can get the brick, I can swim up, and I can pass my swim class. And I always dive exactly to that spot, and I always reach for the brick, and of course, nothing was there.
Nope. It
Right?
moved.
The brick had moved on me, but really what had happened was refraction had taken place. My swim instructor didn't bother to tell me about refraction. He was just worried about me getting the brick from the bottom of the pool.
Do you think he knew about it then?
Not this guy, no.
Oh, okay.
So what of course is happening is, this is hard to draw, but the same applies if you were to like go fishing with a spear or something. Okay, you see the object here. Now if you take aim at this spot right here, and you're standing up here, you're looking down. Okay, because you're in the air and the brick is in the water, the light is bending to you. In reality, the brick is here. So I needed to jump in and aim closer to the wall so that I could land right where the brick was. The show I watched called Dual Survival. A couple of crazy guys running around nature doing stuff. The one guy who I didn't think he was too bright at all. He actually explained refraction without using words like refraction. He's like, if you go spearfishing, you can't aim here. If you see the fish here, you have to aim here if you want to eat that night. And he was able to explain why it took place without using a lot of big physics words. The last thing we want to talk about as it relates to refraction is refraction leads to this thing called total internal reflection. And your instructor should have set up a demonstration for you to see this in two ways. The coolest way to see this is to get a tank of water, okay, and it's relatively still and calm at the top, and to get a laser to shine through it. And if you aim the laser beam straight up, I guarantee you that most of the light will leave. If you aim it a little off to the side, I guarantee you that some of it, most of it will leave, and some of it will kind of travel across the top. If you change that angle and go shallower still, okay, at some point called the critical angle, theta c, so this is called the critical angle, the light will travel all of it right across the top. None of it will leave. And there's another angle, anything beyond the critical angle, so you go shallower still, all the light will reflect back. And we actually use this in technology every day in the form of a fiber optic cable. And so this is how telecommunications work. So inside of these cables are these tiny little, it's a material, it's a transparent material, but the laser hits it in just the right angle every time so that it just bends and goes around the cable. And you don't have to worry about it leaving the cable, you don't have to worry about it stopping or getting stuck. And that light, of course, light is information. You know that because your cell phones are emitting microwaves and radio waves, and that's just information for us. So what I encourage you to take another look at or to think about is the demo that your teacher does where there's a tank of water, okay, and we've got it filled up, and we let some of the water shoot out to the side, and on the other side we're going to hit it with a laser, and I want you to think about what happens next. So you need to be paying attention in class. You need to tell me what happens with this, and this is probably an opportunity to write down some observations as well. So check that demo out. I think that's a worthwhile watch. I believe that covers, yeah, that covers refraction, and that covers total internal reflection. A couple, I guess maybe another item that we wanted to discuss is up here. I was very vague about the type of material. The reason why there's more bend is because of this thing called index of refraction. And it's just a ratio of the speed of light. So it's a ratio of how fast light is traveling in a vacuum, so that 300 million meters per second, to how fast it's going when it's in this material. So that number is always going to be bigger than 1 because this is as fast as it can go. And this is based off something called Snell's law, which is really not important. It just talks about refraction, how light bends in transparent mediums.
Okay.
I think that covers it then.
Yeah.
Signing off, this is Mr. White.
Mr. Johnson.